So good morning, my name is Seiishi Suzuki. I'm from the Institute of Building Structure and Structural Design, and I'm very glad to be here today for presenting the paper titled The Design Implications of Form Finding with Dynamic Topologies. The aim of this research is the development of a methodological approach for the activation of metric and non-metric design spaces during form finding. So in order to do so, we propose to categorize form finding approaches as geometric-driven and topology-driven. And the main difference between both approaches is how data is activated during form finding. So the motivation of this research starts from the study of bending active and form active structures and all hybrid byproducts, mainly because of the wide space for shape exploration that these structures provide. At the moment, we are focused on the study of textile hybrid systems that combine tensile membranes with elastic rods. That means 1- and 2-dimensional elements. We all know that the design process of these structures is not trivial and requires a shape optimization process called form finding. Regardless of the use of different numerical methods, all process needs a static and an initial and static topological model in order to execute the algorithm. Because of this, the designer needs to solve the topological model before starting the form finding process. The problems start appearing where more complex material articulations are involved and designer intuition cannot provide a valid solution. In such cases, the topologic model is solved through the use of extensive studies on analog models, which also means that we need additional amount of manual computation when increasing the complexity of the system. The common approach behind is that numerical form-found geometries can be easily variegated by the dynamic calibration of metric parameters without altering the topological model. That means that from a topological viewpoint, the input model is the same as the output model. Because of this, these strategies are suggested to be categorized as geometric-driven. So in this case, the main assumption is that these conditions simplifies and facilitates stability and convergence of numerical solvers. During the conceptual design stage, form finding needs to support enhanced user model interactions. And because of this, dynamic methods have become important, given the capacity to produce this kind of real-time interactions. In the diagram, we can see the current state of art of form finding tools that can be easily integrated within architectural design practices. In any case, active topology modeling is not fully explored. Actually, when looking for examples where dynamic topology models are an important feature, we need to see for surgical simulators. Since the 90s, in medical fields, the use of computational models has been integrated in order to simulate complex routines for train and prepare surgeons. Due to faster developments, we can see that these models have been extended into more immersive design spaces where the user has the capability to interact with a virtual organ in order to produce real-time geometric and topological responses. Taking all this in consideration, what we are proposing is an alternative computational design methodology that looks for increasing the design space freedom and flexibility through the activation of topology modeling during form finding. In order to do so, we develop a custom form finding tool using the classic force-based schema and implementing 3 types of numerical solvers that provide different results in terms of accuracy. The activation of the topology modeling immediately breaks the linear workflow of geometric-driven approaches. So when such a characteristic is activated, we suggest to categorize form finding as topology-driven. In this case, contrary to geometric-driven approaches where form-found geometry is only variegated, we can say that in topology-driven approaches, form-found geometry is also differentiated because the input model is radically different from the output model. In other words, the main driver here is topological differentiation. In topology-driven form finding, the workflow is circular and recursive with highly interconnected design stages. These stages address the creation and generation of the creation and management of data, the control of the rate of interactivity and accuracy of the simulation, and the taking of decisions in complex design spaces. Because of this, we can regroup in these stages the main problems that we need to face when confining with dynamic topologies. The first stage addresses the appropriate design of a data structure and network model. Common implementations are mainly focused on the efficient storage of data without further specifications for increasing the flexibility of the model. An example of this is the use of the general and static network model. And in order to activate this dynamic topology modeling, we propose the design of an evolving network model with multiple dimensions. The idea behind this network model is that mutable and multiple connections can be are allowed between each pair of nodes, and that different kind of relationships are established between the dimensions. In this case, each node represents a particle, and each dimension represents a network model. In addition, we have marked all the nodes and the edges with unique key identifiers in order to facilitate topological operations while keeping track of all changes occurring in the network. The network is designed with 2 dimensions. Such dimensions are the force topology network and the mesh topology network. And each dimension can be redefined by the user during the form-finding process. In addition to this, nodes are extended with additional information for describing its states within the network. And they are also color-coded in order to visualize such states, as you can see in the diagram. Both dimensions of the network can be used as a graphical interface to interact with the model. In fact, the natural way of interaction has been always at the level of the mesh topology network, but with this model, we can also interact locally and globally at the level of the force topology network. We mentioned about the states, so all the finite states of the nodes constitute the vocabulary of the network, from where axioms are formulated. And from here, user-defined rules are triggered by such axioms in order to conduct safe topological transformations. In this case, rules are the mechanism to secure and guarantee numerical stability and convergence of the system. A predefined catalog of rules has been designed in order to conduct these safe topological transformations, although further operations can be implemented only if such operations are presented in the form of a rule. The second stage that we need to address when confining with dynamic topologies is how this data is generated. In this kind of circular and recursive workflows, the meshing process is completely integrated during the form-finding process. In this case, the topology progressively grows by adding new elements. Because of this, the main problem to face is that we need to guarantee compatible meshes or the construction of compatible meshes. Following this logic, we can create very complex topologies by adding rather simpler meshes. The core idea behind this is the continuous creation of quad meshes, of regular quad meshes, because we prefer the use of quad meshes here because the 2 local directions of the mesh can be directly associated with the weaving directions of the tensile fabric, and because quad faces can be easily converted into triangular ones. 3 types of algorithms were used or select in order to conduct different kind of meshing procedures within different boundary and different recurrent boundary conditions. In this case, we have the boundary conditions are defined with different levels of constraints, which is mainly determined by the number of fixed nodes on the polygonal boundary from where the meshing process starts. For unconstrained conditions, where a minimum number of fixed nodes are on the polygonal boundary, we use a Cadmul-Clark subdivision process. For semi-constrained conditions, where we have like half of the nodes are fixed on the edge, we use a direct method for computing the local UV values and generating quad faces. For fully constrained conditions where all the nodes are fixed on the polygonal boundary, we implement advancing frog method that for paving rows of quads along this polygonal boundary. This is most critical condition because in this case we need to evaluate mesh conformity at every single node on the polygonal boundary. The use of these algorithms was selected in order to support this recursive and circular nature of the topology-driven form-finding approach. And as you can see in the image, these complex topological meshes can be created by adding and joining simple meshes. The next stage to address is the expected diminution of interactivity when massively increasing the size of the system. In this case, it's really important to consider the computational cost that each element requires. In doing so, we propose a multi-scalar modeling strategy for simulating coated membranes. The strategy is based on the construction of a hierarchy of elements that enables an interactive shift from one element to another during the form-finding process. The idea behind is that linear elements like springs and cables are among the less expensive elements to compute, but they provide a rough approximation when simulating coated membranes. To simulate or to have a more accurate simulation, we need surface elements like the constant strain triangle. The problem is that despite that these elements has different topological requirements, the problem is that surface elements tends to be numerically unstable when active modeling is enabled. To face this problem, we propose to conduct initial studies on shape exploration by using systems of cables or springs, and as soon as a satisfactory shape is attained, to dynamically shift to surface elements. This is only possible because quad elements can be easily converted into triangular ones. The problem here is that since we have different meshing algorithms, data is sorted in different ways, leading to unsuitable combinations for applying the surface element. To face this problem, we design an automatic process of edge categorization, always leading to suitable triangulations for implementing the triangular element. The process is an iterative process that starts categorizing edges and sort data in such a way that all the diagonals of the quad faces are aligned and oriented in the same direction that is required to create the seams for the constant strain triangle. In this case, all these operations happens at the level or occur at the level of the force topology network without explicitly altering the mesh topology network, and because of this, a reverse shift is also possible. Here is a video about regarding the dynamic shift of elements, and you can see how different equilibrium conditions are created by applying this shift of elements during the form-finding process. The final stage addresses the problem of taking decisions in complex design spaces that dynamically evolve. You can see in the image that the force topology network becomes almost intractable when the size of the system grows. And this is a very important problem when we try to address further topological operations. In order to face that, we have proposed the use of two types of studies. The first one uses multi-agent-based systems. In this case, we have designed two types of agents, parent and child, each one with very specific behaviors. The parent agent floats around the digital space while dropping children and connections between them. And the designer can place some static targets around this digital space in order to control the openness and the closeness of the structure. All the children from one parent shape a family, and each family represents the network model of an elastic rod. In the same time, the behavior of children is activated in order to search for potential partners based on distance constraint and the range view of the agent. As soon as a potential partner is found, a tensile connection is created and the equilibrium system is changed. In this case, in this case, for example, the designer has a limited control of the form-finding process because the form-finding process is mainly driven by the agents. The second stage, or the second approach, uses machine learning algorithms. In this case, we implement a decision tree algorithm in order to assist the creation of rod-to-rod connections between a disconnected set of rods. The decision tree algorithm throws a positive or negative output regarding the creation of the connection by evaluating an input with a predefined sample pattern. Such a predefined sample pattern consists of a sorted collection of particles that describe the desired pattern of connectivity that needs to be propagated within the network. Each time that the designer calls for assistance, a decision tree structure is created, and the program asks the designer to specify the sample pattern. The computer then starts throwing a random numerical configuration, and it's the task of the decision tree algorithm to evaluate if such numerical configurations are appropriate configurations for propagating the sample pattern around the network. So, as a conclusion, form finding with dynamic topologies is not trivial and requires to address different topics that are regrouped in 4 stages, which are data structure design, discretization, interactivity, and decision making. We consider that even if the implementation is more harder, topology-driven form finding extend the design space freedom and flexibility. Because of this, we also consider that topology-driven form finding is the closest approximation to physical form finding, where material behavior and organization is inseparable. Although we also consider that further research questions needs to be answered. At the moment, we are also conducting the development of a similar multi-scalar modeling strategy at the level of the beams. So in order to shift from 3 degrees of freedom beam to 6 degrees of freedom beams. And we are starting to conduct studies for extending the computational model into more immersive digital spaces. Thank you very much.